disappointed.
It's nice. Yeah, you went whole hog.
Yeah.
This is always like the most awkward part of any class. Like this happens to me all the time because I get everywhere early, and then there's like the 10 minutes where you're just like staring at this audience that's like not ready to hear from you yet. I don't ever know what to do about it. I just sort of like babble, but I don't know if that's the recommended solution.
Just babble.
I mean, most of my teaching is 90% babble. I don't know if you guys would agree, but there's a lot of. Whenever I stream from home, we do a different animal. I get to show them. So we had bees last time, I think. That didn't sting me at all, which was unfortunate.
What, you had a real bee?
Oh, I have a beehive on my porch.
Oh, really?
Yeah.
Like that you want to do that?
Yeah, I made it and put it there, and then I eat its honey.
Really?
Dude, do you not know about my like weird farm issues?
No, I know that something about chickens.
I do have chicken. I have 6 chickens in my guest bedroom.
In your bed?
They live there.
Okay.
Yeah.
You don't do like the little shed out in the yard?
They're legal. It's illegal to have chickens in Baltimore County. And so if I am caught with these chickens, I will face a $12,000 fine.
No way.
That's what the judge told me the last time they caught me with them. So
in your house.
yeah, but they can't come in and check. So I got the chickens inside. I had to move the rabbits inside because they kept escaping because they hate living. All my rabbits have escaped up until now, so the rabbits are with the chickens right now.
You have horses.
I don't have any horses. No horses. I got bees though. Those are deliberate bees.
Are you allowed to have bees?
Bees are fine. Bees are fine. Like chickens, no way. But bees on my porch, like next to some children, is fine. I don't know. The chickens have been the least problematic of my pets. But yeah, I get like 6 eggs a day, which is pretty legit.
The way that I actually go, I'll actually later. And then today I had 4,000 to 5,000 liters. For 3 or 4 eggs. It's like getting different. And then I'm waiting on you to hopefully get some leads from the OS right. So I don't have to okay, good. I got one to you afterwards. What do you leave for the
Wait, where'd you go to undergrad? Wait, what? Oh, I didn't know that part. I knew you were doing a master's in stats out here. I didn't know you went to undergrad here. Wait, what the hell? When?
all of it.
So we were here at the exact same. What did you study though?
Psychology.
Oh, okay. So nothing related to this.
Nothing really.
No wonder I have I've never seen you.
Sometimes
Wait, how did you end up?
Oh.
How did you end up doing any of this?
It's a long story. We don't have that. Probably takes longer than 5 minutes.
Yeah, probably don't know if you want to shout it in front of the class either. But okay, well that's crazy. Did you live in any of the dorms or anything?
Yeah, I lived in a couple of them.
Which ones?
I
I want to estimate the odds of me having walked past you at least once.
We can talk about it later.
Okay, I was in sus for 4 years, so.
Okay. The whole time?
Yeah, I love sus. I was right by the dining hall. I don't know.
Yeah. Cool.
That's really confusing and strange.
It's a wild ride. So you guys went over this stuff before, right?
So we kind of quickly went through perceptrons, backprop nets, and then I gave a basic understanding of CNNs, but probably anything you say will at least be good review.
Cool. Okay.
It's not to the point where they're gonna be like, oh, backprop again.
Yeah. Did you guys go through the backprop calculations? And
No,
stuff?
no, I was like, you take a derivative,
Oh,
and then
okay.
that happens.
All right. So that part might not make as much sense, but it's okay. It's your class. It's your class.
I think there were some equations on the PowerPoint. I think that is about as close to the math as we got.
Okay.
Mostly because, like I said, every time I teach it, I have to relearn it. It's kind of a pain in the ass to understand.
Annoying, yeah. I think I've only done it once by hand.
What, you've done it by hand?
Yeah.
Wow.
Or like a small network.
The way I learned backprop is when I was like a little kid. I was like, I don't know. My dad just like handed me a printout of a Pascal implementation of a neural network.
Really?
He was like, figure out how this works and make one.
Oh.
And I was like, oh, okay.
Rough childhood.
Man, you don't know the half of it. But I finally got it together, and it actually could recognize digits. It was actually really cool.
Oh yeah.
Yeah. I made like a visualization of the training that like I would show people, and they'd be like, "Oh, you're a genius." And I'm like, "No, it's just the visualization's total bullshit."
Yeah.
But people really love like circles with lines flickering rapidly.
Mm-hmm. Well, that's the best thing about these algorithms. People think you're a genius, but it's doing all the work.
Yeah. Yeah, that's the problem with like decision trees. Is I'll like show them to a client, and they're like, "Well, I could have done this."
Yeah.
Like whatever. Next time I'll. Thanks.
Yeah.
All right, well, this looks like who we got. All right, so everyone, welcome to class. Today we are having a guest lecture. I am actually really excited about this. I actually don't know how this is Florian, right? Okay, cool. Look, I just want to make sure I don't like introduce you as like Florian or something. This is Florian. He is one of my coworkers. He is apparently, as I just found out, a UMBC alum and is currently getting his master's in stats here. He does a lot of deep learning stuff. I think just mostly as like a hobby, but like he's really good at it. That's what sounds like it.
Well,
I don't know. You've like done some Kaggle stuff, gotten pretty high scores. So I'm kind of impressed. So yeah, I am. This is probably one of the most exciting lectures we've had so far. I'm excited to learn stuff. So cool. I don't know. Is that everything?
yeah, that's good enough.
Cool.
All right, cool. So yeah, we're going to talk about convolutional neural networks specifically. So I guess you guys touched on some of this stuff before, but I'm going to go through. I'm going to kind of start out with like some of the, how everything works and the intuition, because even if you have heard it before, sometimes it helps to hear like another perspective on it and stuff like that. All right, so let's just get to it. So I call them ConvNets. It's just quicker. So they're basically a specialized type of neural network. So they're particularly well suited to data that's like organized in a grid-like pattern. So think of things like images or time series or like even words and sentences. So any kind of data where like if you have things next to each other, that's significant in some kind of way. So if you think about a picture, like all the pixels that are near each other, they're related to each other somehow. So things like that. That's what these networks are really good at dealing with. So on the right we have a couple of let's see, of like the more well-known architectures. So at the end of the class, I'll try to go through all of these and kind of explain how they all work and like the intuitions behind why people design them the way that they do. So the top one is called LeNet 5. So that's a really old network before all of this stuff kind of kicked off in 2012 and got really popular. So it was made for like recognizing handwritten digits and things like that. So you can see that there's an A there because it's recognizing the letter A. The middle one is called GoogleNet, or you might see it referred to as like InceptionNet. So it looks really crazy and scary, but it's not so bad. We'll kind of break it down. And then the bottom one is sort of my drawing of a thing called a VGGNet, but we'll go through that all later. So, all right, so what makes these things so powerful? So with a typical neural network, we call all the layers like fully connected, and that's because if you have a whole vector of input data, the next layer of neurons, or each neuron connected to every single one of your pieces of input data, right? But with a convolutional network, it's not really the case. So we have these things called kernels, which we'll go through on the next slide. But you kind of have like a fixed number of parameters that you set up in the beginning, so that it's not going to explode with your input data. So let's see. So I guess that's it for that. Okay. So the kernels. So let's see. little square on the right, we'll call that the kernel, and let's say that this is your input grid of data. So basically what we're doing is we're taking those kernels and we're sliding it across the input grid in every unique position that it can like occupy. So this is kind of a little diagram of the I guess the way that we'll do that. So if we have W, X, Y, and Z in the kernel, and then we have A, B, C, or A, E, and F in the input, so that will be the first little square that the kernel will cover. We'll do an element-wise operation, so we'll multiply the first element in the kernel and the first element in the grid there, and then we'll add all of those up. So you can see that in the top left box. So we'll get a single number from each one of these operations. So the kernel actually, it contains all of the weights that we're going to learn. So if you think about the normal like multi-layer perceptron, you have one weight for every connection, and those are the ones that you're learning as you're going through backpropagation. So here we're doing it with the in the kernels. So yeah, I mean, if you're doing this on text or time series, instead of a two-dimensional grid, you can think of it as a one-dimensional vector, and you kind of just slide the kernel down the line there.
So you're just basically like plotting the input square with the kernel.
Yeah.
Okay.
Pretty much. Well, not quite, because then you get a 2x2 if it's a dot product.
Got it.
So think about it more like an element-wise thing.
Yeah, that makes sense.
Yeah, okay. So is that clear? Cool. All right, so let's see. Yeah, so I mean, that's why I have that star there instead of the dot. Okay. And then we also have a bias for each kernel. It's optional, but there's no reason not to use it because it helps you. It'll help the weights learn some more interesting like decision boundaries and things like that. Bias. Okay, cool. So this was supposed to be a cool animation, and it is working, so I'm psyched about that. It wasn't working on my computer, so great. So yeah, so if the yellow square is sort of the kernel, right? It has like 1, 0, 1, 0, 1, 0, and then 1, 0, 1. So it's going through each unique position in the image, and then it's performing that operation. So what we get out of that is we get what we call a feature map, which is sort of a smaller image that is a result of whatever weights we have in the kernel. And those are going to be really important later, these feature maps, as we call them. Because what will happen is the kernel will become things that are trying to pull out significant features from the image. But we'll see examples of that. So yeah, I mean, this is pretty cool animation of how that would work. So far, so good? All right, awesome. So it's kind of a recap of what I just said. So we're just sliding the kernel around, and then for every operation, we get a single number, and we organize the numbers in the same, like we organize them spatially in the same way that we took them out of the image from. So we're not messing with the like the spatial structure of our input data, because it's important. So if we're dealing with images, we want to keep that information. All right. So, and then what we get out of that is a sort of a tweaked version of our image based on whatever the kernel operation is. So, okay. So just like with a any kind of neural network, it's sort of a chain of functions, right? So the output of every layer becomes the input to the next layer. So what we're doing is we're taking this tweaked version of the image, and then we're going to give that to the next layer, kind of as the as if that was the first image that it was seeing, the same way that the first layer works. Okay, so yeah, I mean, you're free to like stack up these convolution layers about as deep as you can go. And we'll see that you're kind of limited to how deep you can go based on how big the input data is, or the size of the image. So there's some operations that downsample the image. So eventually you'll kind of get to 0 dimensions and then you run out of information to process. So, but if you can get around that, you can pretty much go forever with these. So it's common to put a whole bunch of kernels in each layer because each kernel will sort of try to look at the image in a different way, if that makes sense. Yeah, we have a good example of that here. So this column of little images here are some visualizations of kernels from a trained neural network. So what ended up happening was some of the kernels were activated for edges at different orientations. So we have kernels that are looking for horizontal edges, vertical edges, like slanted edges, and we have kernels that are looking for different colors and sort of where different colors come together. So what happens is, like let's say we take the vertical edge kernel and we start to slide that across the image. So that kernel is looking for every place in the image where there's a vertical edge, right? And then the feature map that it's going to pull out of that is kind of an image of all of those vertical edges within the picture. And then you can say the same thing for every single other kernel. And the amazing thing about this is this all just comes out through backpropagation. So all of these weights were initialized randomly, and then through training they became differentiated, and you know they're actually like really smart things to look for in an image because.
So I actually have a question about that. Does it ever happen that just like two kernels end up the same? Or just like two guys who really like vertical lines?
Yeah, I mean we see that a little bit here. So you have this one that's kind of slanted, and up here there's another one, and you can see like there's a couple vertical ones.
Okay, I guess it's just vanishingly unlikely for it to be at least exactly the same.
Sure. Yeah. It's definitely likely. So if you're doing a really simple data set, so maybe just like the hand-drawn characters, I think it's very likely that a lot of your kernels will end up the same.
Okay.
If you have a huge number of them,
right? Because
there's only so much information to extract.
Okay.
But yeah, I mean the weights are initialized completely random, so you know you should get a good set of differentiated kernels. Some of them might be the same. But yeah.
Just a question: how do they how do you visualize the kernels? Like, you know, that's a visualization of the kernels, but like, how would you get that?
You just pull the weights out and you just look at it like an image. So like these could be 7 by 7 pixel images, and it'll look like that.
That's cool.
Yeah. There's a couple other like really cool tricks you can do for the deeper layers because things get a little bit more abstract as you move down the neural network. So instead of just pulling the weights out and looking at them, you'll sort of push an image into the network and then see which parts of the image are maximally activated by that kernel. So, and then you can make a visualization out of that.
So is it ever useful when you're working with this to just like visualize your kernels, or is this just for presentations?
This is useful. So if you visualize your first layer, it looks like this, you can be reasonably sure that your network is learning, you know, some useful things.
Cool.
For the other things, there's some better ways to kind of evaluate it, but they're really fun and cool. If you wanted to make a neural network to generate images, I think it makes a lot of sense to look at the activations of things because you want to make sure that the layers are attending to useful features like, you know, faces or wheels if you're making cars and things like that. And any other questions about this? Okay, cool. So yeah, all right. So here's some examples of like potential feature maps. So these aren't taken from a neural network; they're just like edge detectors. But you can imagine that this is sort of what they're looking like. Right, so if we have just vertical edges and we're looking at a face, the feature map is going to come out like that, which is like a face made out of vertical edges. So you can see wherever there's horizontal lines, it's kind of invisible to that kernel in the network. Cool, so if you are going to stack a bunch of kernels up together, like let's say you had 12 kernels in your first layer, and each one is looking for a different type of edge. Basically what you're doing is you're teasing apart that image. for the following layers into sort of its significant parts, right? So it'll get an image of just vertical, it'll get an image of just horizontal, it'll get an image of maybe color blobs and things like that. So it's sort of like, it's trying to break down the image into what's important. All right. So, yeah. So just like I said, the first layer is typically things like those edges and colors and patterns. Maybe we saw a couple like the textures, again, like the grid here. So, you know, it kind of tears the image down into those fundamental pieces. And then the next layer will sort of combine those together. So it'll take different edges of different orientations and kind of look for shapes, maybe like squares, circles, you know, things like that. Or maybe look for edges that are confined by different color blobs or something. So we're trying to, we start out tearing down the image, the basic steps, and then the next one will kind of go one step higher and kind of put it together in different ways. And it moves to that until we get to the, you know, like a high level representation of whatever we're looking for. So yeah, I mean, a couple of examples, like if we're looking for bananas or oranges, we're going to be looking for like round shapes versus straight shapes, and yellow versus orange, things like that. So the network will attend to what's important in your classification problem, if that's what you're doing. All right, cool. So another operation that's really important is pooling. So like I said, we want to look for more high-level features within the image as we go through the more computations. So if we are looking at the full dimensions of the image at all levels, we're not really going to get like a good zoomed out view of what we're looking for. So we're not going to be able to put all of those features together into something that makes an object. And also, we can start to sort of build way too many parameters, and we'll kind of slow everything down. The operations will sort of go to a crawl. So we use pooling a lot of times for this. So there's a couple different kinds of pooling, and it's basically just like a statistical summary of local regions within our feature maps or images. So a really popular example is max pooling. So let's say we have the square on the left as our image, and then if we have a 2 by 2 square that we're max pooling over, so we basically will plug that square on the image, and we'll take the you know, the highest value out of that region, and we'll use that as our only value for the next layer. So you know, here it's taken out 6, and then 8, and then 3, and then 4. And it's sometimes a good idea to overlap them, but most of the time you won't see that. So you know, these pooling layers aren't going to overlap because, you know, if we did the middle one, we would get 7 out of there instead of you know, 6 and 8, and we'd get a 3 by 3 grid. So most of the time they're not going to overlap. Yeah.
Stride how far it moves.
Yep. Stride how far it moves. Yeah. So yeah, if we did stride 1, it would just move over 1 little block each time.
You get a bigger matrix for the next layer.
You need a smaller matrix. So
Stride is lower.
if the stride is lower, you'll get a bigger matrix than you would with a higher stride, but you're always going to get a smaller matrix than the original.
Right.
Okay. Yeah. So if it was stride 1, you get 3 by 3 out there.
Right.
Yeah. Cool. Yeah. I mean, so that's a really basic operation. Just taking the maximum value. All right. So there's a couple of intuitions about this. So like I said, we kind of want to zoom out as we're going through the calculations, because we don't just want to know where the edges is. We want to know like where the objects are in the image, and we can't get that if we like focus on tiny pieces of the image at a time. And then another thing is that you know, computers are only we only have so much memory and everything, so we want to keep the parameters down a little bit. So it helps kind of speed things up because we're able to cover more ground with less parameters. And there's sort of a potential downside here, is that if we do max pooling over a region with 4 values, we're essentially throwing away 75% of our activations. It can be a good thing and a bad thing. So sometimes you like, well, I'm throwing away a bunch of my calculations, and they can be useful. But also you're sort of forcing some sparsity into your model, which can help it to like generalize a little bit better. There are alternatives to pooling if you don't really like the idea of throwing away a bunch of your computer's hard work.
What are the alternatives?
You can do another convolutional layer with a higher stride. So it's kind of projecting the image down to a smaller space instead of just squeezing it.
Cool.
How do those alternatives kind of like function compared to pooling?
So at the end, I'm going to go through some of the architectures, and the one that's sort of state of the art right now, it doesn't use pooling because it uses the convolutions, but it also had a pretty big jump in, and some other really significant jumps. So it's hard to say whether that was a significant factor or not. But it doesn't seem to be as necessary as people thought, and it's likely that we might see pooling go away. But for right now, it is a popular thing that people are doing. Right. So putting it all together, this is kind of a standard way that you'll usually see it. So we'll stack a couple convolution layers together, and then we'll do a pooling, then a couple more convolution, and then we'll end with a fully connected, which is just kind of like a standard multi-layer perceptron, which you guys saw before, and then your classifier layer or regression layer, or whatever you're trying to do. So for the convolutional layer, like I said, you pick a number of kernels, and typically you'll see things like 32 or 64 kernels. And we try to keep it as like a factor of 2, and that's just because of the CUDA code that we use is kind of optimized for factors of 2. So you'll see like 16, 32, and 64, things like that. So I mean, it just makes it go a little bit faster. Nobody wants to wait for models to train. So yeah, you'll maybe do like 2 layers of 32 kernels to kind of tease apart the image, and then you'll get 32 feature maps coming into the next 32 channel convolution layer, and then that one will get 32 feature maps to the pooling layer. And you squeeze those down, and then you keep going. And I guess I should stick to my example. So it's 64 instead of 32. And then the next one, typically what happens after you pull it, people will double the number of kernels that they're using. We're going to have now 128 kernels looking at like higher level features in the image. All right. So cool. Yep. So like, let's say that we start with like a 32 by 32 by 3, because the images are the tensors, because they have 3 channels for red, green, blue. Then we'll push those through the 64 channel convolution, and then we'll get a 32 by 32 by 64 image. So 64 feature maps, pulled out of that 3 channel image, and we just keep going with that. So then the next layer will downsample it to 16 by 16, and then we'll downsample it by 8 by 8, and then we'll give it to the yeah, and then this is just sort of a recap of everything I've been saying. We just keep squeezing down the image and looking at big parts. All right, so far so good with everything. Okay, so the way that we train a ConvNet is pretty much the same as a multi-layer perceptron or a regular neural network. So we're going to use stochastic gradient descent and backpropagation. There's a couple little things that you have to do differently. But since you guys didn't go through like all the calculations for backprop, this might not make as much sense. But so because of the pooling layers, you can't really if you're throwing away 75% of your activations and you want to take the derivative through the pooling layer, you can only update the weights of the layer that was chosen by the max pooling function, right?
Quick poll. Who remembers what backprop was supposed to do? Like what it was trying to do?
Okay.
A little bit. So basically, you have your result from the neural network, and then you want to go back through the network, assigning, I guess, blame, you could say, to different weights.
Sure.
And then you can, once you can do that, you can take a derivative and then, basically find out how to tweak the weights to make the error go down. Is that a good summary?
Yeah. Do you guys want me to talk about that, or do you want to skip it?
I mean, I don't know if you have thoughts on it, you should say them.
Is it kind of how/why there's bias in the kernel and like how we like work with that? So like on the different feature sets there.
Do you mean the bias weight? Or
Yeah.
Yeah. Okay. So, are you guys cool with like linear regression and logistic regression and stuff? Okay. So if you like have points like this, right? So you have like x's or whatever in circles. If you don't have a bias, your decision boundary can only come out of the origin, right? So like your bias is your y-intercept. So think about it like that, like a really basic, mx plus b thing. Is that right? Yeah.
Yeah.
So if you have a bias, you can come out of the kind of like the top of the, I don't know, you can come out of the y-axis somewhere. So that's really the point of the bias. It allows you to be more flexible with how you're separating the data. So, like I said, it's optional, but I mean, if you don't need it, it'll train to 0. So why not have it? Yeah.
So should you go and try to do that from kind of like each of the pooling layers, or should you just try to move the pooling layers somehow?
Do you mean like when you're doing the backpropagation steps? Yeah. So what you're going to do, so you're taking the derivative with each function with respect to the output of the function before it, right? So what ends up happening is the weights that are not contributing to the so for this first one, if the 1, 1, and 5, those weights are not contributing to the end output of the network, right? So they're not going to be updated in backpropagation. So we're basically just ignoring them because they weren't chosen, I guess. So that's sort of another, maybe it's a downside of pooling, but so the only thing that really makes that a headache is that you have to keep track of all your indices and everything when you're doing backprop. But the good news is you're never going to do it by hand because every library that you use has auto differentiation. So you set up your function and it'll do it for you. But if you wanted to do it by hand, that's how you do it. Cool. Yeah. Any other questions about that? Okay. So I have this one, and I'll skip that. It's basically just saying what I just said. And also sometimes people rotate kernels 90 degrees, so you just have to rotate it back if you're doing that.
At least one person saw those equations and their heart started like pounding with like math-related PTSD.
We're not going to worry about it. But it's basically the same thing, right? So you're just kind of finding the derivative as with respect to each layer, and then each layer is building the output for the following layer. So you're just kind of taking it apart as you're going through. All right, so I'm gonna get off of this. You guys cool with that?
Sure. Yeah.
Okay. All right, so we'll go to the network case studies now. So this is way more fun because these actually do stuff that's interesting. All right, so like I said, this is LINET 5. So this was a really early network. I think I want to say it came out in '98. Let me check the notes. In the '80s, so I'm wrong. So this is the one for like recognizing handwritten digits and things. So this is a problem that the post office was really interested in because they wanted to read all the addresses that people are writing. And that's a lot of work, and people have terrible handwriting. And if you can get a machine to do the easy ones, then people can do the hard So this was something they were working on. So you guys know who Jan LeCun is? Yeah. Okay. So this is his work. That's why it's called LeNet 5 for Jan LeCun. Anyway, so he's kind of a big deal in the deep learning world. So he came up with this architecture, and a lot of people kind of followed this basic design because everybody knows him. So it's characterized by the alternating convolutional and pooling layers. So the first kernel size is 5 by 5. So you can see in the corner, think about like a 5 by 5 kernel, like looking at that section of the image. And then he's got, let's see, only 6 feature maps. So there's only 6 kernels there. So this is kind of small by today's standards. But then again, you're only looking for like lines and things, so it's not really a whole lot of data to tease apart. And then he's got a pooling layer, and then another convolutional layer, and then a pooling layer, and then a final convolutional layer, and then the multi-layer perceptron. And then the output, he's got 10 outputs because it was made for classifying digits, but for some reason the example has an A. So I don't know why that is happening, but if it was letters, it would be, what, 26?
Yeah.
Yeah. So, but yeah, so it's a really popular data set, the MNIST data set. And you can, yeah, anyway, so that's pretty much it. It's very simple. Good. Right. So the next one, this is AlexNet. So the first thing to point out is I didn't mess up the image. It's like that in this paper. I don't know why he didn't take better care of it. Because this paper's been cited like a ton of times. So okay, this network's a really big deal. So this came out in 2012 for the ImageNet competition. Are you guys familiar with that? Yeah.
We can stand here about it again.
Okay, so it's like in the computer vision community, it's this database of like millions of images across 1,000 categories. And every year they have a competition. It's hosted by Stanford. And people will submit their entries to classifying each of the 1,000 categories. So before this network, the error rate, so how bad they did on all of the categories, was about 28%. And they scored by top 5 errors. So within your top 5 guesses, if you don't have the correct label, it's kind of wrong. So it was 28% before that. So AlexNet came out, and then he got the error to 15.4. And the only thing he did was put a convolutional neural network on the data set. So what everybody else was doing before that, they were trying to do, well, they were working really hard, and they were being very smart, and they were sort of trying to extract features from the images and use those to classify them. But Alex was thinking that he'll just be lazy, make his GPU do it with a neural network, and he crushed everybody. So this was a really big deal because the second place was at 20% error, he had 15% error. So it's kind of unheard of at the time to do that well on this data set. So after this is when everybody got very excited about deep learning and neural networks again, because it's finally something had proof that they actually work, and they work really well. So there's a couple other really cool things that he did, and some things that make it look really complicated. So he's got like this branched architecture where it sort of like splits. And the only reason he did that is because GPUs at the time did not have a lot of RAM. So he couldn't fit the whole data set in it, so he had to split. It's not actually like a special feature of the network, it's just a hardware constraint. But he basically did what the LeNet 5 did, except kind of scaled it up a little bit. So in the first layer, he's got 48 kernels instead of just 6, because he's dealing with natural images, so pictures of animals, cars, and things like that. So there's really a lot more in those images that you need to tease apart. Then he did the pooling after that, And then he did 128 kernel convolutional layer, another pooling, and then 3 convolutional layers stacked together, and then a max pooling, and then finally the fully connected layer. So I think I don't remember how long it took to train, but it was a pretty long time, maybe like a week or 2, just in his bedroom, and then he beat a bunch of really smart people, which is great. So, and then the other thing, let's see, did you guys cover like activation functions for like neurons and stuff?
We did, but like all things, it's probably worth talking about again.
Okay, so typically before this, people were using sigmoid activations or TNHs. These kind of look like this, right? So sigmoid is minimum 0, max at 1, TNH is -1 again.
So this is how your node would know how on or off to be. Like it would get this incoming signal and it gets squashed into one of these curves. Oh, sorry.
No, that's cool. So yeah,
Does this one use a different activation function?
yeah. So he uses what they call ReLU, rectified linear. So it's basically just like it's thresholded at 0. So if the well, let's just call the dot product. If the dot product is below 0, he just gives 0 as the answer. If it's above it, he gives whatever the answer is. So it's kind of like a linear, or like it's almost like having no activation unless it's below 0, and he just caps it there. So what that does is it allowed his network to train significantly faster than it would with one of these activation functions. I think it was like 6 times as fast with no loss of accuracy. So, which is great because I think another reason that these weren't so popular is that people didn't really want to wait weeks for a result because they got stuff to do, they're busy. So this makes it a lot more, I guess, like easy to use. You know, if you get results faster, you don't forget what you were trying to do in the first place. And you can do more experiments and things. Okay, so then the next one. So the VGGNet also, this is a pretty significant network. It has a really beautiful architecture. So I should go back to AlexNet real quick. So AlexNet, they changed the kernel sizes throughout the layers. So I think he starts out with like 11 by 11, and then he does like 5 by 5 and 3 by 3 for the end. So there's a lot of stuff going on. Like he really, like he makes a lot of architecture choices as he goes through the network. So VGGNet, they decided they're only going to they have 3 rules basically. They're only going to use 3 by 3 kernels. So really small kernels. They're going to double the number of kernels they use every time that they max pool. And they're going to stack a couple kernels together, or convolutional layers together before they max pool. So it's really just kind of like streamlined and nice and easy to understand. So this was the top performer in 2014. We're skipping the top performer in 2013 because it's really just a tweak of AlexNet, and they just kind of looked at it and thought, pinpointed some places where it could be improved. And the error went down a little bit, but not very significantly. So with VGGNet, so not only is it a great and easy to understand architecture, but they also brought the error down to maybe 7%, I think, 7.4. So almost,
pretty rapid series of decreases there over 3 years.
Pretty awesome. So blew the, yeah.
So then what was the top performer in 2014?
The top performer was that GoogleNet, and I'll go over that next. So that really crazy looking thing. So VGGNet, a single VGGNet actually outperformed the GoogleNet that year, but their submission, they used a whole bunch of them together. So they kind of squeezed out VGG. So for that reason, this is actually more popular for people to use than GoogleNet because individually it was a little bit better. And it's easy to understand, so you're always going to use something that's simpler if it works just as well. But yeah, we'll go over that one next. So let's see. Yeah, so they had a lot of really cool insights here. So by only using 3x3 convolutions, they really trimmed down on the number of parameters you can use to cover the same amount of space. So what they found and what they show in their paper is that if you stack 3x3 convolutional layers like one after another, it's equivalent to covering the same ground as a 1 7x7 layer, except it uses what 81% less parameters. So that's great because you really don't overthink. That's always a problem. And I guess that's all there is to say about it. It's pretty simple, so not a lot of details. Any questions about that? Cool. All right. So GoogleNet. This is the one that beat out VGG, and it's kind of scary looking. So what they did is they have this so this diagram at the bottom is just one of these little blocks, right? So they're stacking these little blocks together, kind of the same way that we stack those basic convolutional layers together. And what this is it's really just, instead of stacking the layers together, they kind of have them all next to each other. So they'll have like a 1x1 convolutional layer, and a 3x3, and a 5x5, and a max pooling. So it's the data as it comes into that layer, it's being branched into 4 different places instead of like a sequential thing.
So how does it get sort of combined back into the filter?
So you can either just, I think they concatenate it. So I mean, because if you have a 3x3, and let's say you have 16 kernels there, right? Then you have 16 feature maps. But if you have a 5x5 and 16 kernels, you have 16 feature maps again. So you can just put them together and then get 32.
Okay.
Their idea was that different size kernels have different strengths, right? Oh, sorry, go ahead.
I was just going to ask about the 3 different endpoints.
Yeah, so those are actually the outputs, and you can sort of, I don't know exactly what they did, but this is 2014, but I think they averaged them together.
So the way this works is if you have a very deep network, as you go back, your error decreases. You get less and less, well, your brain decreases rather. So the early layers take a long time to train. As a result, the late layers can't really work on these kind of low-level abstractions. So the whole thing takes months to train possibly.
Yeah.
If you have an error source from the middle, you can kind of speed up the learning for the early layers. It's not quite as good an error. So basically, like those last little bits before the yellow, the blue ones, are those kind of FC layers. Or no, the yellow is the FC, the blues are the last convolution. So performance classification, that's kind of a lot worse than the full network, but it gives you an error source to update the other part of the network. And over time, you then get the error source from the very, very, very end on the right-hand side, which fine-tunes the network.
Yes.
That's a pretty good answer. Thank you.
Yeah, cool. Good. I didn't know that, so I didn't really pay attention to GoogleNet that much, but awesome. Yeah, so, and that works because like you lose the derivative as you go deeper and deeper. So that's just the nature of it. So does anybody else have any questions? Okay, cool. So, all right. So then this is the first place from 2015. So this one brought the error all the way down to 3.4%, I think. So this is a residual network by Microsoft. So I'm going to steal a lot of their slides because they're a lot better than the ones that I would make. Yeah.
So I actually have a question. Like when you're, so I don't know if you have any intuition about this. When people are making these, like what on earth is the process? They're just like, is there intuition behind like, oh, I think it's doing this, so I think it needs another convolutional layer? Or are they just like, I don't know, let's just put in 8 more convolutional layers and see what happens?
Yeah, no, there is. So this one, they had a really good insight. I'll try to touch on it a little bit. But for the GoogleNet paper, so I mean, obviously I'm not knowledgeable about GoogleNet, but they did a lot of work to try to like really study like what's going on in the network, and they like it looks really crazy and scary, but they really put a lot of thought into into how these things are going. So, I mean, I'd say check that out if you want to get into insight into like the thought processes and things. Okay, so yeah, so the residual network is really cool. So they kind of took the philosophy that BGGNet had and they put a little twist on it. In 2015, there's a couple of different big competitions, and they took first in all of them with the same basic architecture. So, all right. So one thing to point out is that it's massive. So it's 152 layers compared to GigaNet, which is 22, and BGG, which is 19 or 16, depending on which variant you're using. So they, we'll get into it in a bit, but they had a pretty specialized trick, or they had a really clever trick that they used to train networks to sleep. So, you know, like he was just saying, with the GigaNet, at the successive outputs, it's really hard to train deep networks because you just can't really get the weights to update, you know, that far down. So, you know, GigaNet got around that by training in steps like that. Is that right? Mm-hmm. Yeah, cool. But these guys, they figured out that you can just add these sort of like skip connections, and then you don't need to worry about any kind of like branching architecture and anything. You can do everything just like BGG, which is stacks of 2 convolutional layers and then downsample. This is a good, this is directly from their paper. So they showed that like if you use a plain net without this residual unit, if you do make it deeper, your error gets worse. And that's because you just can't train it. It just doesn't work. But then with the residual networks, you can keep going deeper and your error gets better as you go deeper. So, and that's kind of what you would think would happen, right? If you have more, you know, more computational power, more power to like represent your data in smarter ways, your error should get better the deeper it gets. So, you know, people weren't saying that, but with residual networks, you do see that. So, what does it look like? I'm going to steal the author's joke here. So, just like this in the slide, and then it looks like this. So, it's graphic, right? But basically, it's very simple. So, each one of these little blocks is, they're all almost identical. So, we'll just go to one of the blocks here. So, with a basic network here, so you have a weight layer, which is a convolutional layer, and then it goes right to another convolutional layer, and you just kind of keep stacking those together. So what they did instead is, instead of learning the new way to represent the data as it goes through, what they want to do is they want to learn what you want to add to the original data. So they have this like this skip connection. So so X is the input data, and then f of X is the result of the 2 convolutional blocks. So what they're doing, the output of their residual block is the output of the convolutional block plus the input to that convolutional block. Does that make sense? Cool. So the reason that's so successful is that when you are going through like the backdrop calculations, if you come to an addition, like what will happen is the gradient will kind of just like skip all this stuff and it'll go straight to the next block. So you have a way for every block to kind of have access to the error signal from the end of the network. And then, you know, it still goes through each weight layer just as strongly as it would at the last layer. Yeah. Okay. So yeah, it's super deep, and it's very simple. It's just like stacked convolutional layers, just like BGG. They mostly use 3x3 convolutions as well, except for the first layer, which is a 7x7, and that just helps you get your memory footprint down. Yeah, and like I said, they have those skip connections. So with this one, you're basically just limited to how many times you want to copy and paste your code. Well, how deep you can go. So, and then there's the last one from this year, which is the, this is actually the second place from this year. I didn't see the solution for the first place. But the error rate is only about 3%. So I think there's a lot more interesting things to say about the data set itself than this network. But it's basically sort of a combination of the ResNet from last year and the GoogleNet. So they have the same thing with the branched architectures, except that the branches are sort of symmetrical to each other. So they're basically taking the residual block and expanding it into different branches. But anyway, so with the data set, it's it's millions of images and thousands of categories, and they're estimating that human error is about 3 or 3.5%, and I mean that's basically what we hit last year. So I think that we sort of maxed out that data set because this could be way better, but if we're kind of at the bottom of the error percent, it's hard to tell. So I mean, all these images were labeled by Mechanical Turk, and if there's 3% error already built into your data set, then it makes it really hard to kind of evaluate these things. So there was not a lot of buzz around the results from this group because of that.
So are they gonna just shut down? Are they gonna keep doing the competition, or?
I don't know, but I don't know if it makes sense.
Yeah, I feel like we just need a new data set.
Yeah, so Google put one out. It's even bigger. And another thing is like, ImageNet has a lot of dog pictures. So if you guys saw those images that were generated by Deep Dream, there's a lot of dog faces because all those networks are trained on ImageNet, which is like overrepresented by dogs. So that's why it turns everything into a dog. So this new data set should be a lot more balanced and representative. And yeah, I think. Yeah, but I mean, in applied work, your data set is going to be more important than your model. So this is a good example of why that's true. You can make something that could possibly be amazing, but you don't know if it's better than the data. Yeah.
So before all the compilation, they were kind of working to extract stuff. Has there been any work into looking at different ways of kind of pre-processing the images to make them and then parsing it using these, or is it all more just improving the model? Because I imagine their perceptual color spaces and stuff, which are a lot better at detecting how something looks and stuff.
Yeah. So pre-processing used to be a little bit more important than it is now. And that's because people came up with more clever ways to initialize the weights and things like that. So people just put a lot of thought into how to pre-process it and to get the best performance. But one thing that people do now a lot is that they sort of augment the images as they're coming. So because what you have to do is you have to cycle through your data set a whole bunch of times, right? So if you're showing it the same exact picture in the same exact way, it's not quite as effective. So let's say, let's say we have a picture of this water bottle and we want to show it to the network. I don't want to show it to the network the same exact way every single time. I want to kind of rotate it around, flip it, maybe mess with the color channels a little bit. So you can still tell what it is, but it's sort of in different, simulate different lighting conditions and angles and things like that. Does that answer your question? And another thing that people have looked at is, so a lot of times the filters will look the same in the first layer. So some people thought, well, maybe let's just initialize those layers like that. But I think it might train a little bit faster, but I don't know if it gives you any benefit because they're going to come out anyway. Yeah.
Is there any ranking used by training time as competing against accuracy? I might be happy with 70% if I can have it tomorrow.
Yeah.
90%.
Yeah, totally. Not for these competitions, but I mean, if you're working, so a friend of mine is working on something where they want real-time object detection, right? So it needs to go 30 frames per second on a video feed. So they're not using this massive network. They're using something a lot more similar to maybe like AlexNet, something that's really small. So like you're saying, it's pretty good. This was revolutionary at the time. So like it's good, but it's not amazing, but it gets the job done. So yeah, I mean you're gonna choose your based on and like these are like research. So they don't care about time, they care about state of the art. What's that?
As long as it's done training for the grant money.
Exactly, yeah.
So are things like Alex, like what is kind of the, like what do modern computers kind of like do like pretty quickly? Like you said, like some of AlexNet we can now do very fast.
Yeah,
Like is BGGNet now like kind of doable in a fast amount of time? So,
BGGNet's like pretty slow. It's very like memory hungry. So the amount of time depends, right? So if you only have a couple images coming in per minute, you can really run most of these. But as that scales up, you can be careful about that. And there's also a lot of work in like decreasing the footprint of each model, like after it's trained, things like that. So there's a lot of different things that you can do. So yeah, you still have to take it as it comes. Each problem.
I have a bunch of general questions actually. So you've worked on a bunch of like sort of deep learning problems.
Yeah.
Before, what is the process? I guess like where do you start and what tools do you use? And so I know Keras is a tool for this.
Yeah.
But like so, I've been trying to work on the Kaggle fish competition, and I got as far as opening Keras and being like, I want a convolutional layer, I guess.
Yeah.
So like I don't know what's involved.
Okay, so yeah, that's awesome. That's a good question. So if you're doing classification, all of these models are typically released like after they've been trained on the big massive data set. So what they end up doing is you can download them with all the weights already trained in there. So they become really good like general classifiers. So they're good at looking at natural images across a broad range of categories. So so like what I would do is if I had time, so I'm doing the same thing, right? So I took a ResNet that was pre-trained because we don't have to go fast for that competition. And I trained it on those images with a very small learning rate because you don't really want to tweak the weights like too far out of where they are because they're already pretty good in general. And you just sort of fine tune it on your data set. So, I mean, one way to think about it is like it's forgetting about like trucks and cars and dogs. And it's focusing on fish.
Okay, I didn't know you could like partially retrain these.
Yeah, so there's like a rule of thumb that people sometimes do is like a learning rate 1/100th of what they used in the original paper. So take your network, look at the paper, see what learning rate they use, go 100th of that, and you don't really need to do it a whole lot. Maybe just a couple of iterations through your data set. Because really, I mean, you just want like the low-level features is going to be the same for everything. Like everything's got edges, everything's got colors, things like that. So you really just like the higher level layers. You want those to become more specific to your problem.
Man, I have like a whole list of questions, but I want you guys to. So I know these things get used for like audio because it's time series. Text and pictures seem to be like the big three.
Yeah.
Are there any other like major use cases you've heard about, or it's usually pictures, text, or sound from what I can tell?
Yeah. Do you have an answer to that?
I was kind of wondering a second ago whether they might apply it to like microwave laser images, like airport scanners, those new ones. I was kind of wondering if you could use those in that regard.
Maybe.
I mean, I don't know if it would work on data because it's kind of an image, right?
Yeah, I don't know what that data looks like. If it's like, I mean, if it's got like a spatial aspect to it, or like neighboring, like I said, like neighboring points are meaningful to each other, then it could work. So I mean,
Yeah, I think other sensors are really good
yeah,
use case for this. I just haven't heard about people using them that way.
yeah. I mean, you can use it on like EEG signals.
Okay.
You know, because it's a time series and the data that's next to each other are related, and, you know, things like that. So I mean, it's almost like a like putting a filter on a waveform, you know,
Cool.
and seeing how you can tease it apart.
Anyone got any other questions? Cool. Let's clap because he's a guest. Thanks a lot, dude.
Yeah.
For the rest of you.